Hi everyone, welcome back. So we've collected our SART data now. Let's have a look and see if we have significant results. Now, our hypotheses were, is there a relationship between errors made on the SART and the cognitive failures questionnaire? And another question we wanted to ask is, was there a difference in performance on the SART, either the fixed or the random SART, between our different groups? And in this case, we were looking at a kind of mild cognitive impairment and dementia group, an elderly group, and a young group. So we have three groups, and we want to see if there's a difference between them. But let's start by pre-processing our data. And you can see what the data looks like here, and you can see the little thing that we added into our key press has worked nicely. So when you press the space bar, it always says that's correct, except in threes. If you press the space bar when it's a 3 trial, it will automatically mark the response as incorrect. So in order to find out these, what we refer to as commission errors, which are the times you press when you shouldn't, then what we can do here is count the number of times the word incorrect shows up. I'm going to start building this by making a pivot table. Don't forget as well, we're also going to make a version of this with an R script afterwards, and there'll be some advantages to using RStudio, which I'm going to talk about in a little bit. So first thing first, we pretty much always add our private ID into the rows column. And this is basically going to give us all of our individual participants. Now, what we need as a value is the response. So you can see if I go back here, it is the response column that has correct and incorrect labels. So I'm going to drag response into values. What we can also do is we can add response into columns. And now you can see that it's split up responses as correct or incorrect in each one of my columns. Now, the first thing, and it's always a good idea to have checks in your data. You need to know a bit about your experiment so you can find out if something's gone wrong. One of the things we know about this experiment is there are 225 trials. So the grand total should never be higher than 225. And I can see here, for example, this one is 628. So what on earth has happened with this participant? Well, if I look back at my data, first of all, what we can see is that we have a combination of practice and task, and we're including both of those things in our data. So one of the first things we should do is add a filter to make sure that we only end up looking at the task data and we don't include the practice trials. So I just need to add type into filter, that's come up here. Now I just say only look at task. So that reduces the numbers to some extent, but this guy's still way over what we should have. There are way more responses than you would expect to see. So there's still something going on there. Before I get onto that, this is just a reminder. This is where adding these variables into your spreadsheet is so useful, because we added that type column to indicate practice and actual task-based trials, and that means that in a pivot table like this I can easily filter out those practice trials and not include them. It took 2 clicks. So it's a good idea to think about metadata in your spreadsheets. What I'm actually going to do now is I'm also going to use this same sort of filtering idea, but this time I'm going to apply the filter and only look for that one participant. So now each one of these columns can be used as a filter. So if I go here to my participant, and I only want to include this participant, the one who ends in 8501. And let's have a look at their data. See if we can find anything unusual. And I'm starting to see something unusual straight away. See here, they got incorrect, but they've got incorrect 12 times. And what's happened here is the person has started repeatedly tapping. So they're not tapping once, they keep tapping. It's a common thing to find with participants. You get double tappers. With hindsight, this could have been something we could have fixed with piloting. Piloting, we could have probably, if we piloted 10 people, someone probably would have done this, and then we would have known to correct it. Simplest way to correct it is just to tell participants, give them better instructions. I should have given them better instructions to say, just press the one time. Even if you do that, though, people will get excited. You can see that Gorilla under this column here, attempt, has actually numbered it, so 1, 2, 3, 4. So we can use that information to scale it back. Again, what we do is we add another filter. So this time I'm going to use attempt, and I'm going to say I only care about attempt number 1. And now you can see that number has dropped down dramatically. It's still bigger than it should be. It should be 225. So something's still not quite right here. Something's gone a little bit wrong. And if I go back and I look at the data again, I can actually apply the same rule to the data in here. So I can say, only show me the first attempt. And I know this from spending a bit of time looking at the data. What you find later on, here's an example. So you can see on these, see how it says 6, 6, 7, 7, 8, 8, and 9, 9. So it's a variation on the double tapping. You actually saw it in the last thing I showed you as well. See how here, this is the trial number. These are trial number 96. The way that we set up the task, participants had to press a button as soon as the number came up. And then just to kind of count, if they weren't able to press as quickly enough to see when the button came up, we also let them press when the mask came on. So what's happened here, when you have a double presser, is that they get a response scored in the number, and they get a response scored in the mask. So they end up getting 2 responses for each one of your trials. Now, I have to be honest, I haven't been able to figure out a way to fix this in Excel. There probably is a way to fix this in Excel with duplicate trials, and perhaps it could involve writing an if statement, where we, on this column, would say something like, if this number is the same as this number, then skip it. And we would only then get correct trials. Actually, I've just come up with that now. That might be a good fix. Let's have a look and see. So we can say equals if this trial equals this trial blank. Otherwise, we need it to be the actual response variable up here. So that's now marked as correct. This might not work. So when you drag down formulas, when you try to drag formulas, it obviously tries to be clever. And because there are a different number of presses, what we can see has happened is that the formula doesn't necessarily line up. Okay, so that's a nice idea, but it didn't work out in practice. I'm going to show you how to fix that though when we get to R, because in RStudio, it took me 1 line to fix that, so it was much, much easier. For the moment, it's hopefully we've done a lot to correct the problem, and we're aware of the problem. So for the time being, I'm just going to carry on as is. As I said, I'm going to show you how to fix it in RStudio. Now the next thing I want to do, because we don't know which group people are in, and that's quite useful information. So I'm going to go to here, participant starting group, and I'm going to add that in columns. And now we can see that we've got correct MCI old young, incorrect MCI old and young. So we've split up the data. Now that I have that, I can start doing a bit of copy and pasting. So I'm going to make a new sheet and copy that in. And then we start adding in labels, for example, ID. And I saw from beforehand, this first column is the MCI people. So I can type MCI and I can just drag that down here. This was the young participants. So I can drag that down here. And then the last ones were the old participants, and I can drag that down here. And there we go, I've got my group identifier. Next thing to do is to just drag these so they're all in the same column. So that goes there, and that goes there. This we don't need, we can delete that. In fact, what I'll do is just drag all of this across. And now we just need to do the same thing again. So drag those two across, drag this one across. And there we go. And we can see there are some gaps in the data. Those gaps are there because the answer is 0 in the count. There wasn't a single time. This person is an example of a perfect participant on the fixed SART. They pressed 200 times, meaning they pressed for every single one of the correct numbers that was not 3, and they never pressed when it was a 3. So this is a perfect performance. And we can see a couple examples here of perfect performances. I'm going to call this correct, incorrect, and then we would repeat this procedure again with the next data file, which would be for the random SART. This was for the fixed SART. Now the other thing you might want to do as well, we had a hypothesis about the questionnaire, the cognitive failures questionnaire. So at this point we just need to say here equals sum, and we're going to add all of these quantized values. So remember, this is a short form file. Short form files mean that each column was one of the questions in your questionnaire, each row is a participant. So all we have to do is keep adding all those bits together, and imagine we have done that, and then we just double click and we drag that formula down. So now we would have the scores for everybody. Something to bear in mind here, and this is all, again, knowing a bit about your data really helps here. So the actual task, when you see the scoring, they scored 0 for never, and then they scored 1 for very rarely, and 2, 3, and 4. So it scored from 0 to 4, and what you can see, just even in this column, you can see the Gorilla has scored from 1 to 5. So everything has moved one place bigger. So what we have to do to get the correct scores here is subtract 1 for every question. So we subtract 25. So this equals this minus 25. Now in this case, that's obviously a negative number, but when you added everything together, you'll have a positive value. And that is your score. Remember, when you're merging data sets, so when you're merging the commission errors from random and fixed SART, and then when you're also adding in the cognitive failures questionnaire, always include the ID code as you copy and paste. Because by including the ID code, you can make sure that you've got exactly the right person's data. Because the order that the data is shown here might not be the same as this order. But if you copy the ID codes for different participants, then you'll be able to double check and see that these things match up. So here's one that I made earlier on. It's the questionnaire. We've got what we call the omission and commission errors. Omission errors is where you don't press for the random SART. It's not quite right here because actually what we've just got here is a count of correct. I didn't bother with it because it had the double tap issue. We are going to look at omission errors in the next video when we work with RStudio because I can correctly calculate it there. The commission errors should be correct. The commission errors are every time they press on a 3. And we have that for the random and the fixed SART, and we know what group they're in. So our first question was about the relationship between the questionnaires and commission errors. Now to look at this, I go to regression and correlation, and I can add in my variables of interest up here. We can also look at our assumption checks, and I can see that these violate the rules of assumptions. It's not surprising. With questionnaires, it is most common to use Spearman's row rather than Pearson's R, because there are questionnaire scores they don't meet the parametric assumptions. So mostly when you're doing questionnaire work, you need to use Spearman's row anyway. What we can see, I'm going to tick here to flag correlations, and I'm also going to tick these buttons underneath to give me some nice scatter plots to visualize the data. What we can see is that it doesn't matter whether you use Pearson's R or Pearson's row, there is a correlation between the random and the fixed SART, which is a very sensible thing. It's a positive correlation as well, which is, again, it makes sense. People who make more mistakes on the fixed SART also made more mistakes on the random SART. I actually get rid of those density variables ones. So that's a very sensible result, this positive correlation. However, we don't see any relationship between errors on the fixed and random SART with the cognitive failures questionnaire. One thing that it can be important to do here, and you can't do this in JASP, which I'm quite surprised about, there is something you can do called a partial correlation. And a partial correlation allows you to basically run correlations for different groups, or you account for the fact that you have different groups in your data. And you want to see, is there still a correlation once I deal with the fact that I have different populations in my data set? If I go on to descriptives, I can actually look at the scatter plots in relation to the different groups. It's quite easy. I click my variables up here, and I add split by group, and then here under plots, I can just click on scatter plot. And it's starting to create those scatter plots in here. You also get, which is quite nice, these density variables on the top and on the right. And these density variables basically tell us about the distributions of data. Now by default, it's added a smooth regression line. I'm going to make it a linear line. It's easier to interpret in these cases. And what we can actually see is there does appear to be a positive relationship between the number of errors and the performance on the cognitive failures questionnaire in my old population, but not in my young and my MCI groups. And this could be something you could explore, so you could actually filter the data so that we only look at the elderly individuals and see whether the correlations still stand. That's very easy to do in JASP. We click up here on the filter label, and we just have to make a rule that says group equals, and here I'm going to say old, and I apply that to my data. And you can see everything now is grayed out in here, except for my old participants. And now you can see that it has automatically recalculated the assumption checks, but also it's automatically recalculated all of the correlations that I put together earlier on. So if we look here at the cognitive failures questionnaire, we can see that actually it's not significant. It's got a reasonably strong positive correlation of 0.4, but that does not reach significance. It's 0.07. So it's data in the right trend, but again, we can't make a big inference because it doesn't meet the criteria for statistical significance. So I think we've dealt with hypothesis 1. We weren't able to support it fully, although it looks as though there is a trend in our elderly data. But then again, we need to be very hesitant when we talk about trends in that way. It's something for a student project, I think you can get away with discussing it. Remember, I haven't put this in there, when you're reporting correlations, you need the R value and the P value and the number of participants. So those are the things you'll need to include when you're reporting your correlations. Now, what I've done here is I've just dragged the filter into the little bin and I've clicked apply. So we've removed that filter. So we're back to having all of our participant data. And now I want to say, is there a difference in my two groups? And to do that, I'm going to use a classical ANOVA. And here I need to have my dependent variable, which in this case will start with the fixed commission errors, and my fixed factors, which are my groups. And here we can start adding extra elements. So we can add in descriptive statistics, we can add in our estimates of effect size, and we can add a plot with error bars, which is always very useful. So this is all being calculated now down here by JASP, but what we can already see is that there is a significant result. So you can pretty much see why that's the case now by looking at the graph. We can see that in this case, elderly people are a lot better at the SART than our young people and our individuals with mild cognitive impairment. Now, you can obviously report this, and to report the ANOVA, we obviously need the F statistic, we need the degrees of freedom, and I think it's a good practice to now include the effect size as well. The next thing that we can do is we can do what's called a post hoc test. The post hoc test basically is a way of saying, where are there significant differences in my ANOVA? What is driving this effect? From the graph, we can see what it is, but it's always better to have a statistic. And what this has done in the post hoc tests is we're running lots of t-tests, and we're doing a t-test to say, is there a significant difference between the MCI group and the old group? Is there a significant difference between the MCI and the young group? And is there a significant difference between the old and young group? And what we have here is something known as a correction for multiple comparisons. This is a big problem for fMRI, and basically I know statisticians hate this way of describing it, but I think it's the most intuitive way of to make this make sense. When you're saying that you have a p-value of 0.05, you're saying that there is, roughly speaking, a 5% chance that your result is a false positive. It's a false result. That's significance. If you keep doing the same tests, then you keep having a 5% chance of finding a result by chance. So if I do 100 tests and I have a p-value of 0.05, it's saying that 5 of those tests will say there is a significant difference by chance, because there's a 5% chance of finding a false positive. The correction for multiple comparisons deals with that problem, and it changes and adjusts your p-value to say, given the number of tests you're doing, your new p-value to get the same level is the following. And these results basically say we've corrected for it, and there is a significant difference between the MCI groups and your young and old groups, but not between the young and old groups. So in this case, our MCI group is performing worse than young and old. And you would write in your results, you would be able to write this as your t statistic, and you'd be able to explain what's driving this ANOVA. I would always recommend as well including a graph. I think graphs are great, and just being able to visualize it makes a lot of sense. So once we've done that, what we could do is we could just, in JASP, we can click on, I believe it's the plus, yep, and duplicate that, and just run the exact same analysis with the random SART. Another thing you might be interested in doing is what's called a repeated measures ANOVA. And in the repeated measures ANOVA, we're going to bring everything into one ANOVA rather than running 2 separate ANOVAs. And here, what I can do is I can say there is a fixed and there is a random. These are my 2 types of SART. And I can drag those into the correct column. Subjects factor is my group. So what this ANOVA does is it calculates the difference. It calculates the differences between subjects in each one of my conditions, and it also accounts for within subject differences as well. And I'm going to make a graph to go along with it to help us look at our results. And what we see here is in fact 2 significant results. We see there is a main effect of the SART. And that basically means that there is a difference between performance on the fixed compared to the random SART. And we're going to need post hoc tests to really understand that. I'm going to get those running in the background now. But we can see already by looking at the graph that the difference between fixed and random SART is that people on average here made a lot more errors on the random SART than they did on the fixed SART. And if I pull up my descriptive statistics, that's going to validate what we see here. So the average of performance on the random SART is going to be bigger than the average of these numbers. The second thing is that there is also, well, we see here a group difference. So if you average these data points together, it will tell you there is a difference between the different populations. We also have this SART by group interaction, and that's really being driven by this young group. Then that's basically telling us that there's a big difference in performance on the fixed and random SART in young people, and you don't really see that big a difference in the MCI group or the elderly group. And that's what the SART by group interaction means. It means that group is acting as a modulator for the difference between the 2 SART conditions. And you can see here on the post hoc tests which things are significant after correcting for multiple comparisons, where your group differences lie. And they're a little bit different now than from before, because what we see now is that the elderly are significantly different from the MCI, and elderly are different from young. But young and MCI are not different. It's the elderly group who stand out as different now. So these are just a couple ways of working with your statistics and different ways of answering the hypotheses we set out. Is there a difference in SART performance between the different groups? It turns out yes, there very clearly is. There's differences in both the fixed SART and the random SART, and we have this interaction effect that tells us the differences in performance for fixed versus random SART are different between our groups. The last thing as well is that we weren't able to find a significant positive relationship between performance on the SART and the cognitive failures questionnaire. There was a trend towards this in the old group, but it did not reach significance. So what we're going to do in the next video is we're going to look at pre-processing the data in R, and we're going to look at a quick analysis inside of RStudio as well.